Okay, next we will consider one definition. The vectors x1, x2, etc., xn, okay, are said to be linearly independent relative to the subspace E1 subset of E if the linear combination of xi with scalars ai, that is sigma equal to 1 to n ai xi, belongs to E1 implies a1, a2, etc., an equal to 0. Okay, once again, the vectors x1, x2, etc., xn are said to be linearly independent relative to a subspace E1 if whenever sigma ai equal to 1 to n ai xi belongs to E1 implies each ai is equal to 0. Okay, so you might, for the coset you might be knowing, whenever a belongs to h, you have a plus h is same as h, the identity element of that coset, right? So similar, more or less the same idea only, right? See, this element belongs to ei implies we have this whenever this with plus ei will be equal to an identity element. So the same idea. So whenever x1, x2, etc., xn is said to be linearly independent relative to that space, set space means whenever that element, the linear combination of that vectors belongs to that set implies each ai is equal to 0. Okay. Now consider the lemma. Okay, let's suppose the dimension of the quotient space E given E1 is n if and only if there exists x1, x2, etc., xn is linearly independent vectors relative to E1, okay, such that for every x belongs to E, there exists a unique set of numbers a1, a2, etc., an, and a unique vector y belongs to E1 such that we have x equal to sigma equal to 1 to n ai xi plus y. Okay, that is every element in E can be written as sigma equal to 1 to n ai xi plus y. Okay, where ai's are scalars and xi's are linearly independent vectors relative to E1. Okay, now moreover the cosets x1, x2, etc., xn becomes the basis elements for the quotient space E given E1. That is what we have to prove. Okay, so we have last section we have studied what is linearly independent vectors relative to E1 and all, right? Okay, so let us see how we can write the proof. So let us assume that the dimension of given E given E1 is n. Okay, so let first assume that let the dimension of the quotient space E given E1 is equal to n. Okay, that means there exist vectors, linearly independent vectors, becomes n linearly independent vectors becomes the basis. Let us say the coset x1, coset x2, etc., coset xn is a basis for the quotient space E given E1. Okay, now what do you have to prove? You have to prove that there exists this x1, x2, etc. becomes linearly independent vectors relative to E1. Okay, so and also we have to show that. So what is the claim here? Claim becomes, so what's the definition then? If sigma ai xi belongs to E1, we have to prove that each ai equal to 0 for all I, right? Then we will then what do you have? This xi is linearly independent relative to En. So assume sigma ai xi, where I is from 1 to n. So obviously assume ai xi belongs to capital E. Okay, now consider, what you consider is sigma I equal to 1 to n, okay, ai into the cosets. Okay, you consider this. This can be written as sigma by linearity property I to n ai xi. Again by linearity property, what you can write it as sigma I equal to 1 to n, okay, ai xi total cost, which is equal to 0 vector. Why? Why it's so? We know that for a coset, whenever a belongs to h, a plus h is equal to h, right? A plus h is equal to h, where is it is the identity, right? Identity element of that quotient group. So this is becomes the identity. Therefore, what you are getting, which implies sigma I equal to 1 to n ai into coset this one is 0. But each cosets xi, comma xi, x2, etc. is a basis. Okay. So what do we need? Therefore, each ai should be equal to 0, which implies ai equal to 0 for all I. That was our claim, right? So whenever sigma I equal to 1 to n, ai xi belongs to even, so even we have, which implies ai equal to 0 for all I. Therefore, set x1 comma x2 comma etc. xn is linearly independent relative to E1. Okay. Okay, so next, what is your claim now? You can see what is the claim now. So that we have done. Next we have to show that for every x belongs to E, okay, next we have to show that every x belongs to E, we have to prove that there exists scalars, unique scalars a1, a2, etc. n, and a unique vector y such that x can be written as, uniquely written as x equal to sigma equal to 1 to n ai xi plus y. Okay, so let us see how. Okay, next claim. Next claim is that we have to do is like that. Okay, now, so let us assume. Now consider. Sorry. Let's suppose x belongs to E. Therefore, for every coset, x can be written as sigma I equal to 1 is a linear combination of the basis vectors, that is xi. That is what you have assumed. Sigma xi, each x1, x2 cosets are bases. Therefore, every coset can be written as the linear combination of its bases, right? Again, which is equal to, by linearity property, what you have is, which is equal to sigma I equal to 1 to n ai xi. Okay, now, so which implies x minus ai xi, which again can be written as, this can be again written as coset sigma equal to 1 to n ai xi. Okay, so which implies x minus ai sigma ai xi belongs to E1. How? We know that two cosets x equal to y if and only if x minus y belongs to E1. Okay, for E given E1. From that, so this we are getting coset x is equal to coset sigma equal to 1 to n ai xi. So we have x minus sigma ai xi belongs to ei. So which implies there exists some y belongs to E1 such that y equal to x minus sigma equal to 1 to n ai xi, right? So which implies so what we have now, y equal to this one, which implies x equal to, sigma equal to 1 to n ai xi plus y. This is what we have to prove, right? Now next is you can see what is next we have to prove is in your theorem is next theorem we have to prove it as so we have proved x equal to sigma equal to 1 ai xi. Okay, we have to next prove the uniqueness part. Unique set of minimum ai xi there exists, right, for every. So next is the uniqueness part. Okay, so next is the uniqueness part. Let us do. Okay. Okay. So next what you can uniqueness part. Let's suppose there exists. How will prove the uniqueness? If there exists two, then we will both are identical. Okay. So let's suppose there exists y comma z belongs to E1 such that, okay, and scalars bi and ai belongs to F such that x can be written as sigma I equal to 1 to n ai xi plus y, and again x can be written as sigma I equal to 1 to n bi xi plus z. Okay, then what you have on subtracting both sides, we have and sigma ai minus bi into xi. Okay, and next which is equal to on the right side what you have is z minus y, but z is belongs to E1 and y belongs to E1, so z minus y is belongs to E1. But we know that x1, x2, etc. are linearly independent relative to E1. That means whenever sigma ai xi belongs to E1, we have each ai is equal to 0. So we got that sigma ai minus bi into xi belongs to E1, which implies ai minus bi equal to 0 for all I, which implies ai equal to bi. Okay, so this term becomes, left side becomes 0. Therefore we are getting z minus y also equal to 0. So from that we will get it as z equal to, which implies z equal to y. So hence we have proved the uniqueness part. Okay. Okay, now conversely what do we have? Converse part. Okay, suppose conversely assume that we are assuming that there exists x1, x2, etc. xn relatively independent to linearly independent to E1. Then we have to prove that the dimension of E1 is same as quotient space is equal to n, and each x1, x2's coset becomes the basis. Okay, so let us assume that. Conversely assume that suppose x1 comma x2 etc. xn are linearly independent relative to E1, and what you have, every x can be written as sigma I equal to 1 to n ai xi plus y, where y belongs to E1. Okay, for every x belongs to E, we can write it as these are all we have to assume. Okay, what we have to prove is the cosets are cosets x1, x2, xn, xr are basis for this, then which implies that dimension of E given E1 is equal to n. Okay, so see, so how you will do, so let's take sigma I equal to 1 to n ai into the cosets xi equal to, this is how you will show that this is a linearly independent, right? So we have to show that this is basis, so we have to show that it is linearly independent and it spans, right? So it is equal to 0. 0 means 0 element in quotient space, which implies by linearity property we have I equal to 1 to n ai xi equal to 0, again which implies by linearity property well, no, not needed, which is okay, you can by linearity property what you have, the whole sigma equal to 1 to n ai xi equal to the 0 space. Okay, now so which implies we know that whenever quotients, we know that whenever x coset xy is equal to y implies x minus y belongs to E1, right? So what we are having here, therefore which implies sigma I equal to 1 to n ai xi minus 0. Minus 0 means ai minus xi itself belongs to E1. But we by hypothesis what you have, x1, x2, etc. are linearly independent related to E1, and sigma ai to n ai xi belongs to ei implies what you have, ai equal to 0 for all line. Okay, since x1 comma x2 comma etc. xn are linearly independent relative to E1. Okay, so we have proved that, which implies sigma I equal to 1 to n ai, the cosets ai equal to 0 implies each ai equal to 0 for all I. So which implies each cosets, that is the color for I equal to 1 to etc. n is linearly independent, right? Now what you have to prove, so first part of to show that basis, right? So next part what you have to prove is to prove that it spans. Okay, so we have to every element in quotient space can be spanned by this calculation. So for that what you will do, okay, let's assume that let's consider any element in, let's suppose x belongs to the quotient space E given E1. We have to show that it is it can be spanned by the collection cosets xi, x1, x2, etc. xn, right? So collection this belongs to this side. Now we know that okay, then what, let's suppose x belongs to E. Therefore by hypothesis there exists some y belongs to E1 such that x can be written as y plus sigma I equal to 1 to n ai xi, right? That is x minus sigma I equal to 1 to n ai xi belongs to E, right? Which implies what you have, x minus y belongs to even implies that cosets are same, right? Therefore we have the coset x is equal to coset sigma I equal to 1 to n ai xi. By linearity property, what you have, this one which can be written as sigma I equal to 1 to n coset ai xi. So by scalar multiplication, this is same as sigma I equal to 1 to n ai into xi. So every x can be written as a linear combination of x1 cosets x1 x2 etc xi, which implies it spans, right? So collection x1 comma x2 comma etc xn spans E quotient space E. Therefore, so it's we have shown that it is linearly independent and it spans. Therefore what you have, this set becomes a basis for the set. Okay. Therefore the collection, okay, becomes a basis, and we have dimension of E given E1 equal to, okay, so hence proved.